Hello students, my name is Lavanya Krishna. I'm your physics educator for grade 10. Today we'll be talking about a new chapter, magnetic effects of electric current. Before we start discussing this chapter, let's recall what we've studied in our previous classes. We have studied some basics like what is a magnet. A magnet is nothing but a rock or a material which has the ability to attract or repel other magnets or other magnetic substances like iron, nickel. And also we have studied about a bar magnet. When I consider a bar magnet, it has two poles, the north pole and the south pole. And also we know that these poles can never be separated, that is, the monopoles never exist. Even if I cut this magnet into n number of pieces, each piece of that magnet will have a north pole and south pole. They are inseparable. And also we have understood few basic things like poles repel each other, unlike poles attract each other. That is, if I consider a north pole, they repel each other. A south pole, they repel each other. Whereas a north pole, or south pole or a north pole, they attract each other, which means like poles repel each other, unlike poles attract each other. Now that we understood how important it is for us to study this chapter, let's discuss our first topic, magnetic field. What is a magnetic field? It is the space or the region around a magnet or a current carrying conductor is called the magnetic field, and it is denoted by the letter capital B. And to study a little bit more about it, how are this field represented? How does it look like? So the magnetic field around a magnet or a current carrying conductor is given by field lines. These field lines can either be straight or it can be curved. For example, when I consider a bar magnet, we all know it has a north pole, a south pole. Magnetic field line starts from the north and ends at the south. But inside the magnet, it starts from the south and ends at the north. So, outside the magnet, the field lines are curved. But inside the magnet, it is straight. So, the magnetic field can be either represented by a straight line or a curved line. And to talk more about magnetic field is a vector quantity, which means it requires both magnitude and direction for its complete specification. We all know what a vector quantity, isn't it? It is nothing but a physical quantity which has both a magnitude and a direction. And what about the direction of the magnetic field? It is given by the tangent drawn to that point. For example, when I consider a bar magnet, the field lines around it. If I have to know the direction of magnetic field at any point here around the magnet, it is given by the tangent drawn to that point. To understand better, let's consider two more points. So, the direction of magnetic field at these 2 points is given by the tangent drawn at that point. Now let's continue to study about the units of magnetic field intensity. We all know there are two kinds of unit, the SI unit and the CGS unit. The SI unit of magnetic field intensity is Tesla and it is denoted by the letter capital T, and the CGS unit is Gauss and it is denoted by the letter capital G. If you know here, the SI unit is named after a scientist, Nikola Tesla, and the CGS unit is also named after a German scientist. Now let's establish a relationship between the SI unit, that is Tesla, the CGS unit, that is Gauss, which is given by 1 Tesla is equal to 10 to the power 4 Gauss, or you can just write it as 1T is equal to 10 to the power 4 G. Another thing to remember when we are writing the units, if it is named after a scientist, you should always use the capital letters to denote the unit. Now let's move on to study our next topic, that is the properties of magnetic field. What are the properties of magnetic field? The first property being they are always closed loops, which means you should not draw any discontinuity, or there should not be any discontinuity in the field lines. They should always be continuous and closed loops. And the second property is the lines start from the north pole and ends at the south pole outside the magnet. But we all know even inside the magnet it starts from the south and ends at the north. Let's study our third property, which is one of the most important property, that is the magnetic field lines never cross each other. So why shouldn't they cross each other? Let me show you a diagram. Here I am considering two field lines A, B, and these field lines are meeting at a point C. So the direction of magnetic field at point C is given by the two tangents drawn at that point. So at a point you can never draw two tangents. For example, if you are in the middle of the road, you can either go left or you can go right, but at the same time you cannot go in two different directions. The same logic applies here. And also when I keep a magnetic compass at point C, it can deflect either in the direction 1 or 2. It cannot deflect in both 1 and 2 direction. Therefore, the magnetic field line should never cross each other. And the last property being the density of lines is directly proportional to the strength of the magnetic field, which means stronger the field you can represent with more number of field lines. If the field is weaker, you can represent with lesser number of magnetic field lines. Let's move on to study one of the most important topic of this chapter, magnetic effects of electric current. To talk in simple words, what is magnetic effects of electric current? The magnetic field produced around a current carrying conductor is called magnetic effect of electric current. Let us consider a conductor, call it AB. The current flows from A to B. Now, when I place a magnetic compass needle below it, this is the north pole of the needle, that is the south pole of the needle. So whenever there is a flow of current in the conductor AB, the magnetic compass deflects. So why does it deflect? Due to the presence of magnetic field. How is this magnetic field produced? It is produced due to the current flowing in the conductor. This phenomenon is known as magnetic effects of electric current. This was discovered first in 1820 by Christian Ørsted, and the fact about it is it was discovered accidentally. So this gives rise to mechanical forces. Those mechanical forces can be in turn used in various applications. So we know that every time when there is a flow of current in a conductor, when you keep a compass needle, a magnetic compass needle, it deflects. So what is the direction of deflection? That is given by Ampere's swimming rule, which states, imagine a person swimming along a conductor in the direction of the current. Place a compass needle near or below him. His left hand will always deflect towards the north pole of the compass needle, and this is called as Ampere's swimming rule, which gives us the direction of deflection of the magnetic compass needle. In this session, we recalled what we studied in our previous classes, what magnets are, what are the poles of a magnet, and then we studied why do we need to study magnetic effects of electric current. With that, we started our first topic, magnetic field. We studied about the direction of magnetic field, units of magnetic field, and also few important properties of magnetic field. Later, we moved on to the most important topic of this chapter, magnetic effects of electric current. Once we discussed magnetic effects of electric current, we also studied Ampere's swimming rule.